This is the intro video for AP Calculus AB, section 1.3. And in this section, we're going to be looking at how to evaluate limits analytically. We're still going to bring in graphs to kind of help us understand what's going on, but we're going to work on some different techniques than what we've been doing. So just a reminder, the limit of a function as x approaches c does not depend on f of c. It doesn't depend on the y value of the function when x equals c. It's possible that that could be the case in those cases. So we can use what's called direct substitution. These functions are continuous and they're well behaved. We call them well behaved just because they're usually very, very easy to deal with. We're going to find some other functions that are not so well behaved. But let's start off with a well behaved function here. So let's take a look at our first example. The first example says, let's find the limit as x approaches 2 of sine of pi x over 2. So I've drawn the graph over here of that function, y equals sine of pi x over 2. And we're going to note here that when x is 2, which that's 1, that's 2, we're going to note that right around that area, it sure looks an awful lot like this function is continuous. At least visually, that's what it looks like. Oftentimes the calculator is not going to be honest with us. It's going to look one way, but it's going to look like it's continuous, but it's not. In this case, this actually is a continuous graph. So we can use direct substitution to help us evaluate this. So we're going to write then this limit equals or is the same as sine of pi times 2 over 2. So we're just doing direct substitution here. Of course, the 2's cancel out. I'm left with simply sine of pi, and sine of pi is 0. If we go back to the graph to kind of check this out, we can see that the behavior from the left and the behavior from the right are both heading towards a y value of 0. And not only that, since this function is continuous, the value of the function when x is 2 is also 0. So here, what you can say is that this limit equals 0, and because the function we're dealing with is what we call continuous, you could also say f of 2 equals 0. This relationship will not always be the case, and I wasn't really looking for this over here. I was only looking for this, but it's important to note because that function is continuous, the behavior from the left and the behavior from the right will both equal the value of the function at that point. Okay, so let's take a look now at a different function, and as promised, not so well behaved. So looking at number 2 here, why don't you take a second, use your calculator if you want. We're going to eventually graph this without the calculator, but do take a look at and see what this graph of x squared minus 1 over x plus 1 really looks like, and go ahead and write that on your graph. Okay, so I'm guessing that when you graph this, your calculator probably showed you something like, I don't know, something like that, I guess. Yeah, something like that. Seems perfectly reasonable. And so you might be led to believe, like I mentioned before, this would be incorrect, but you might be led to believe that we get this wonderful line right here. Therefore, the function must be continuous, and direct substitution will work great. So let's try direct substitution. When you try that, you end up with negative 1 squared minus 1 over negative 1 plus 1. Okay, so we try to evaluate this, and we end up with 1 minus 1 over negative 1 plus 1. Well, that's 0 on the top and 0 on the bottom. The 0 on the top is not a big deal, but that 0 in the denominator is a major issue. We've got a problem. You can't divide by 0. And so that should be our first hint that maybe there's a little bit more going on with this function than maybe meets the eye. Then, maybe the calculator didn't totally tell us the truth. So I'm going to clear this off. we're going to go back here and do a little bit more investigation. Let's not worry about the graph right now. I'm going to look at this, realizing that when I tried to evaluate this, I had a problem. I had division by 0. If you ever do have something like that, then what we want to do is we want to work on trying to manipulate this in some way, typically using algebra in some form or fashion to try to simplify this. And in this case, factoring is going to be the key. So what I'm going to do is I'm going to write the limit as x goes towards -1. And I'm going to evaluate the numerator. The numerator is the difference of two squares. It's going to be x plus 1 times x minus 1. And then the denominator is still x plus 1. And I'm sure you notice now, of course, that this factor here cancels with that factor there. This leaves me with the limit as x goes towards -1 of x minus 1. And anytime we see something like this, anytime we cancel out a factor, kind of the offending factor, the one that causes the division by 0, we should retry the direct substitution. So this will then give me -1 minus 1, which of course is -2, which actually goes pretty well with our graph. Let's go back to the graph and investigate that a little bit further and see what was actually happening there. As I mentioned, when you graph this on your calculator, you got something like, you got a nice straight line. And I'm going to do this. Oops, I didn't want to do that. There we go. This is really what was going on with that graph. This is -1 right here. What we had is we had a hole in the graph. Whenever you can cancel out a factor in the top and the bottom, what that does is create a hole in the original graph. So what we often do with these graphs is we put this open circle right there, indicating that the original function does not exist right there. So as you look at this, you can see that as we approach from the left, so we approach from the left, we're approaching a certain value. We now know it's -2. And as we approach from the right, we're approaching the same value. So we know that the limit is going to equal -2. We got that analytically. We didn't really need the graph for that. But what I want to do here is compare like we did before. I want to say here that this limit is equal to -2. But unlike before, if I were to look at f of -1, I can't say that f of -1 equals -2 because there's a hole there. So what I have to do is say f of -1 simply does not exist. Like I said, there's a hole there. So if you contrast this with what we just saw a minute ago, you can see why the value of a function, around, at that number we're trying to evaluate the limit at, it doesn't matter. What matters is the behavior. We're simply looking for what's happening from the left, what's happening from the right. And in this case, the answer to both of those questions is -2, even though the function itself didn't exist at -1. This is an example of a function that is not continuous, whereas the function in number 1 was continuous. Okay, we're going to wrap this up with one more function here in number 3. Number 3 is fairly similar to number 2. I encourage you maybe to try this one on your own. Maybe pause the video and see what you can do with it, and play it and see how it really goes. Hopefully we agree. So if you want to go ahead and do that, I'm going to go ahead and get started. If I were to graph this, it's going to be kind of like that situation we saw in number 2, in which the graph on the calculator is not going to be totally truthful. It's not going to be as precise as we want it to be. It ends up looking like this, nice cubic, something like that maybe. It's not a perfect graph, but it's close. Of course, we're looking for what's going on. The limit as x approaches 2. So, maybe that's 1, maybe that's 2, something like that. We might look up there and say, oh, well, look, a nice continuous function. That must be the y value. So I should be able just to, plug in the 2. Of course, when you do that, you get 2 to the 4th minus 16 over 2 minus 2. It gives us 0 on the top, no big deal. 0 on the bottom, big deal. So once again, something that looked continuous on a graph actually is not continuous. And so because we got this 0 in the denominator, we need to go back and do some more analyzing and see if we can figure this out. And like before, factoring is going to be the key. This is a little harder factoring. So I'm going to factor the numerator as the difference of two squares. It's going to be the limit as x approaches 2. Please notice that as I do these steps, the limit is not disappearing. That is super duper important. If the limit disappears, what you're really telling me is that you've done it. You've completed whatever the limit was telling you to do, and we haven't. We haven't done anything with the limit yet. It needs to stay there. Okay, notice nothing really happens with that first factoring. What I'm going to need to do is recognize that that first factor factors again. So it's going to factor as a difference of squares again. So it's going to be x minus 2 times x plus 2 times x squared plus 4 over x minus 2. This allows us to cancel out the x minus 2's. Of course, that's going to create a hole. So there was actually a hole in our cubic. We just couldn't see it on the calculator. All right, so limit as x approaches 2 now of x plus 2 times x squared plus 4 over 1. So now we can try direct substitution. So in doing so, I get 2 plus 2. Notice now the limit is gone because I am evaluating the limit, so it doesn't need to be there anymore. So this ends up being 4 times 8, 32. So must be then that this cubic, let's try that again, there we go, must have a hole right there. So when x is 2, when x is 2, the function itself, the graph doesn't exist. But again, as we look carefully at the behavior from the left and the behavior from the right, we're approaching the same y value, both approaching 32. Therefore, we can say that successfully now that the limit as x approaches 2 of that function is 32. If we were also asked to find f of 2, if the function was called f, most certainly would not be 32, right? The f of 2 would end up being dne. And so because the graph of the function doesn't exist when x is 2, if the limit does exist, we can say that this is definitely a discontinuous function, kind of like number 2. Okay, I hope this is making sense to you. Got a little check for understanding exercise coming up. Why don't you try that, and we'll check your answers here in a second. All right, first question. Hopefully you have these answered. What is a limit? This is not a mathematically precise definition, but it's a good description. What is a limit? It is the y value the graph approaches as x gets closer and closer to an x value. We've also said that it's the pattern of behavior of the function without regard to the actual value of the function at that particular number. Again, we're looking for the pattern of behavior. We're not looking for the exact value of the function at that point. All right. Number 2 says draw a graph of a function that is a point where the limit doesn't exist due to different behavior from the left and the right. So there's my y-axis. There is my x-axis. So if I was going to try to draw this graph, maybe I'm interested in this value here, a. So as I approach from the left, say that the y value is approaching some positive number, and from the right, maybe the y value is approaching some negative number. It's a clear case where we've got different behavior from the left and the right. Okay, number 3. Well, we don't know if number 3 is a well-behaved function or not right away, so let's go ahead and hope that it is. What I'm going to do is try direct substitution like we were doing before. And when I look at this, cosine of 2 pi over 3 using direct substitution, I think this is going to work out just fine. It does say no calculator allowed. That's just an effort to help you try to remember the unit circle. So the cosine of 2 pi over 3, give you just a second to think about that, is negative 1/2. Negative because it's in the second quadrant. Okay, and then the last one, number 4, again, no calculator allowed. And we have no idea if this is a well-behaved function or not, so we're just going to try direct substitution and see if it works. So this will give me tangent of 4 pi over 3 over 2 times 3 squared minus 3 times 3 minus 1. Okay, so our denominator is going to be, what, 18 minus 9 minus 1. That's promising. We know that that's not 0, so that's good. And then tangent of 4 pi over 3 again, unit circle time. Tangent of 4 pi over 3 is square root of 3 over 1, so just square root of 3. So let's see, we end up with square root of 3 over 8. Works out pretty nicely. Okay, so numbers 3 and 4 were nicely behaved. When you come to class, we're going to look at some other examples that are not so nicely behaved, and we'll go from there. Hope this worked for you. See you in class.